Welcome everyone to our webinar. I am Liz Mueller with Carus Corporation. Today our webinar is Landfill Leachate Odor Control Solutions with Permanganate, and we have Mr. John Bull presenting on our behalf. Just a few housekeeping items before we get started. Everyone is in listen-only mode to help cut down on any background noise. Please feel free to enter questions as you think of them into the questions pane that you will find on your dashboard through the Go To Webinar section. We should have time at the end to get to those questions. If for some reason we don't, we're able to see the email address associated with those questions, so we'll follow up with you directly. Today we'll be using the polls feature, so throughout the webinar we'll have 2 different polls that we launch. Today's webinar is being recorded, and we should have that available about 48 hours after the webinar, available on our website, which will link to our YouTube page. And also we'll have a PDF available if you're interested in receiving those. Here's my email address. Please get in contact with me and I'd be happy to share it with you. Throughout 2017, we've had various webinars which we have recorded and posted on our website. Here's where you can access those. Here's our website and then the location. And also be on the watch for our 2018 series that we are working on right now. We will post that as soon as we have it finalized. How to find us. Here's our Carus Corporation website, our general email address as well as mine. And follow us on our social media platforms. We are active on LinkedIn, YouTube, Facebook, and Twitter, where we'll frequently post any upcoming events, trade shows, conferences that we're exhibiting at or presenting. We also have employee and product highlights, technical information, and webinar schedules that we frequently post. And here we're going to launch our first poll. What is your position within the organization? And we'll give everybody about 30 seconds. All right, thanks everybody for filling in those answers. It looks like a lot of us have entered the other category. Welcome everyone. And with that, I would like to introduce our speaker, Mr. John Bull. John is the Global Technical Program Manager at Carus Corporation. John has been with Carus for over 40 years, serving in a variety of sales and marketing positions. The Technical Service Department provides customer support, including on-site lab testing, plant scale startup, and troubleshooting services. John earned his BA in engineering from Purdue University, West Lafayette, Indiana. He is a member of the Water Environment Federation, WEF, and American Water Works Association, AWWA, where he served as the AWWA Illinois Section Chair from 1992 to 1993. And we welcome John.
All right, thanks Liz for setting this up for us, and welcome to all of our all of our attendees today. Today's topic is really kind of a fun one because it's a twist on what is actually a rather old application, which is odor control and wastewater treatment with permanganate chemistries. And today we're going to be focusing specifically on landfills and landfill leachate odors. And this is really almost an industrial type of discharge. So they are subject to industrial pre-treatment discharge standards and NPDES permitting, but also have the issues of odors that are being released when you're processing wastewater. So here's the roadmap that I'm going to follow today. I'm going to start and build a little bit of a foundation and talk about permanganate products for those of you who may not be familiar with them, and a little bit about oxidation chemistry in general. And then we'll move into wastewater odor control and specifically landfill leachate odor control. I'll talk a little bit about laboratory and field testing and how we go about determining the effectiveness of our products in the field. And then at the end, probably the most important part is some of the case studies that we've been doing so we can pass along some real-time information to you on what we're finding. And at the end, we'll just mention very quickly what permanganate feed systems look like. So let's start with permanganate chemistry, first of all. Permanganate really falls into two chemistry buckets. It's first of all a manganese compound, and secondly, it is an oxidizing agent. And it comes in two primary forms, either as a crystalline solid of pretty high purity, usually greater than 97 to 98%, and also now as a concentrated liquid. And the liquids are manufactured in either a 20% liquid concentration or a 40%. The dry crystalline permanganate products are potassium permanganate, and their formula is KMnO4. And the liquid products are made with sodium permanganate, and its formula is NaMnO4. We consider permanganate to be a stable oxidizing agent, which means basically that we can manufacture it, package it, and deliver it in dry crystalline or form or as a concentrated liquid, where the user then can take it out of that package and use it on site. It does not have to be generated at the site where it's going to be used. It is stable. It can be packaged, stored, and delivered to the user. What we are doing is we're taking manganese ore, manganese dioxide, and we're applying oxygen and energy to it in order to manufacture permanganate. What the customer does is takes that permanganate and takes the energy and the oxygen back out again and ends up back where we started from with manganese ore. Now, just a quick comparison between the dry product and the liquid product. And the real bottom line here is that the products are essentially the same, just the form changes. So the active ingredient is the permanganate ion, which is MnO4. The packaging sizes are very, very similar, from small containers to large bulk deliveries. The main difference occurs between the two when we talk about the water solubility. The dry crystalline potassium permanganate has a limited solubility at room temperature, which is about 6% by weight maximum. Now that's a little bit difficult to achieve except with very good mixing and very pure water. So generally in the field, when the customer is using the product and they want to mix up a solution with dry crystalline permanganate, we recommend that they stay within the 1 to 3% by weight range. It's easy to dissolve the product to meet this range, and it's easy to handle. And as I mentioned earlier, the liquid sodium permanganate products have a much higher water solubility at room temperature. We can actually manufacture them to be 50% by weight, and then we dilute them for the customer to either 20% or 40%. So what is an oxidizing agent? In very simple terms, I think the easiest way to describe it is that it's energized oxygen. And in that form, we can use it in a variety of different purification types of applications. Now, oxidation chemistry is very versatile. It's used in a lot of different applications and industries. And for those of you who like to pull a chemistry text off the shelf and read through it, what you'll generally find is that the research work with oxidizing agents involves building something or synthesizing some type of organic molecule. So almost all of what's written in textbooks is about making something else. In the environmental markets, such as what we're talking about today, we're really talking about the other side of that equation, which is to take unwanted or impure contaminants and break them down into something that is non-toxic or non-odorous or easy to dispose of. The permanganate side of an oxidation reaction looks like this. The MnO4 ion on the left represents permanganate, And because permanganate, when it's dissolved in water, has a pink or purple color to it, you can see the MnO4 here is shown in purple. When the reaction occurs, permanganate will accept 3 electrons and end up as manganese dioxide on the right-hand side of this equation, MnO2. The manganese dioxide is a solid material, it's a flock, and it settles out in different types of wastewater treatment processes. Permanganate has a long history of being used for odor control, and that's in part because it is very good at oxidizing specific functional groups on organic molecules. It really likes to attack double bonds and triple bonds in organic molecules, so alkenes and alkynes go very, very quickly. But then there are a lot of side chain types of reactions that can occur as well too, with alcohols, organic sulfur compounds, and organic nitrogen compounds as well. By attacking those functional groups, we can deodorize the molecule and get rid of any kind of unpleasant odors that are associated with it. Now I want to say a little bit more about the oxidation of organics with different types of compounds. So in an ideal world, oxidation chemistry really involves taking organic molecules and breaking them all the way down to carbon dioxide and water. This takes a lot of energy. Sometimes it can involve heat, such as in an incineration process. But in the mild conditions of water treatment and wastewater treatment, this generally does not occur. What you usually find is that large organic molecules are attacked by the oxidizing agent and split and broken into fragments or small partial organic molecules, usually in the form of an organic acid molecule. Now this is great if we're trying to remove toxicity or remove odor, because a lot of these byproduct molecules are non-odorous and non-toxic. However, they still are measurable as organic carbon. So if we're trying to remove total organic carbon or BOD or COD, you see very little change in those types of measurements when you're using oxidation chemistry under the conditions, the mild conditions of water and wastewater treatment. Now there are some very specific organic compounds that can be attacked readily by oxidizing agents, and phenol is one of those. And in the case of landfill leachate, sometimes phenol is present in the wastewater as well. So permanganate, along with other oxidizing agents, does a great job of attacking and breaking down phenol into short-chain organic acids. Now, in addition to oxidizing organic material, there are a handful of inorganic oxidation reactions that can occur to remove compounds from a water supply. And these are shown here on this particular slide, and they are manganese removal, iron removal, the oxidation of arsenic from arsenic 3 to arsenic 5, and the oxidation of hydrogen sulfide. Now this is the one that will be of most interest to us today, because hydrogen sulfide is the primary odor compound that comes off of landfill leachate. Now just a little bit on some background information on wastewater treatment. So you can characterize wastewater, and the contaminants can be placed in usually one of 4 rather major categories. The categories, when we're talking about landfill leachate, of most interest to us is really the dissolved impurities, the organic compounds that are present, and the inorganic compounds, which may in fact include dissolved solids and different kinds of metals. But for today's presentation, we want to look at those secondary types of characterizations, and you can see that odor is a major component of those secondary characterizations. Odors are a problem in part because our nose is very sensitive to them and can pick them up at very, very low threshold concentrations. In wastewater treatment, the ones that we run into most often are the organic sulfur compounds, which are called mercaptans, and of course hydrogen sulfide is on this list as well too. The real important information on this slide is to show you that the odor thresholds are very low when measured in parts per million levels. Hydrogen sulfide, of course, is of particular interest to most wastewater treatment plant operators. Here are the characteristics that are associated with it. It's a colorless gas, so you cannot see that it's present. You need to have some type of monitor present in order to tell that it's there. Although your nose will tell you initially by noticing the typical rotten egg odor that's associated with sulfide. The difficulty with that is that after a significant amount of exposure, your nose can become rather desensitized to that odor, and you may not recognize that it's there any longer. Sulfide is water soluble, and in high concentrations, it can be extremely toxic. Hydrogen sulfide will also dissolve in water on pipes and on metal equipment, and with some biological action taking place, we can form sulfuric acid from that sulfide, and it is very corrosive to different metal parts and to electrical components as well. And in extremely high concentrations, hydrogen sulfide gas can be an explosive. This is a very common chart that you can find in a lot of reference materials that sort of warn you about the dangers of inhaling hydrogen sulfide and associated toxicity with it. The very right-hand column of this chart shows you the parts per million levels of hydrogen sulfide in air. And you can see that even in very low concentrations of 10, 50, 100 parts per million, which are not uncommon in wastewater treatment plant operations, you can have some rather negative impacts on human health. Now, a little bit about testing for and trying to recognize hydrogen sulfide, and how do we do it in the field when we're trying to run a test or determine the effectiveness of permanganate. First of all, dissolved hydrogen sulfide in water can be measured using what is referred to as the methylene blue test. It's a colorimetric test, so what you're looking for is increased blue color as the concentration of sulfide increases in the wastewater. This is a great test. The one that we like using is manufactured by a company called Chemetrix. And the only real downside to this is if the wastewater is highly colored, it's very difficult to use a colorimetric test to determine different types of concentrations. Now, when we're talking about landfill leachate, unfortunately, we're often talking about wastewater that is in fact highly colored. So this test may not be very valuable in these particular types of situations. A much cleaner test, and one that is extremely accurate, is to measure the sulfide that's being released into the air. So we're measuring volatile sulfide concentrations in air using some type of monitoring device, and the one that we use most often is one manufactured and referred to as the odor log. This is a gas monitoring device that not only gives us an instantaneous readout of hydrogen sulfide levels in air, but it can also be used as a data logging device so that we can measure sulfide concentrations over many hours or many days. And you'll see some data later that I'll present that was collected using a gas data logger. Now, we also use this odor log in the laboratory when we're trying to do just simple bench scale testing to determine permanganate demands and permanganate effectiveness. The way we do that is we use very simple equipment. We use a 1 liter plastic container, a jar that has a lid associated with it, and we fill it about halfway with the wastewater that we're trying to treat. So we've put 500 mils of wastewater into it. This allows us to cap this jar and then shake it. And after shaking it for a short period of time, which releases the sulfide into the headspace of the jar, we can take the cap off and place the odor log data analyzer on the top of that jar and actually measure and see how much sulfide has been released. By running this test in several iterations, and where we have treated the wastewater with different amounts of permanganate, we can see that the sulfides are removed, and we can determine to some degree how much permanganate is required to do that. I would say, however, as a cautionary note, that this is a very concentrated headspace, a very small sample that we're measuring. So we get very, very high sulfide levels coming off in this jar. And as a result, it tends to overstate how much oxidant is needed to remove the sulfide down to a low level. So this is a good screening device, but the actual concentrations that we may have to feed or actual dosages we may have to feed in the field are best determined by actually doing a field study. So Liz has another poll question for you that she's going to talk about right now.
Great, so here's our second and our final poll. How did you hear about our webinar today? We'll give it about 30 seconds. All right, we're going to go ahead and close the poll. So it's pretty equally split between receiving our email blast from Carus, referrals, and the advertising that we had done for this webinar. Great, thank you, everyone.
Well, we appreciate you taking the poll because it really gives you a break from listening to me lecture about the particular topic. So we like using them, right? So I'm going to move on and talk now specifically about landfill leachate and odor control associated with that particular waste stream. So the industry itself recognizes that there are a lot of treatment challenges associated with treating leachate, and this actually applies a lot to odor control as well. So I thought I would present those just as background. First, of course, there are variable loads and flows depending on how much rainfall is occurring in the area of a landfill operation. So it can be high flows during rainy season and very low flows during drought seasons. So flow equalization and long retention times can contribute to odor production. Why? Because in a lot of cases, we're collecting wastewater for a significant period of time before it's pumped off site. And during those long retention times, anaerobic conditions can occur and sulfides will be produced by sulfate-reducing bacteria. So the treatment process is often intermittent pumping, and that's not a particular problem except that we should recognize that any type of feed system that we're going to be using should be tied in with those leachate pumps so that we treat only when leachate is flowing. And then in some cases, we can see elevated temperatures in collected leachate, and that contributes as well to odor generation. In a report last year, Waste Management characterized leachate in this particular way, looking at the organic content and also the ammonia content, which are probably important when you're concerned about pre-treatment discharge regulations or NPDES permitting regulations. You'll be very focused on these type of parameters. One of the things, though, that is interesting about this data is that as the landfill ages, the contaminant loading changes pretty dramatically. So the types of problems that may occur will often be associated with the age of that particular landfill. They also reported not only on organic contamination, but inorganic contamination as well. And you can see that there are a lot of metals and other inorganic compounds that can be leached from solid waste and end up in the wastewater flow itself. Of interest to us here, of course, is that it's quite common to see iron and manganese in these particular systems as the leachate is collected. So I'm going to switch over now and talk a little bit about some very specific cases that we've had the chance to work with. So here's a case. You can see the inputs, and this is very typical. The water, for the most part, is collected leachate that is running through an open cell and is collected in some type of large wet well or containment vessel. But then there's often rainwater that is collected from the property, from the perimeter of the property. And in some cases where methane is being incinerated, you can get some concentrated condensate coming off that particular process, but it's generally relatively low flow. Because the flows are rather variable, it's not uncommon to see a large storage containment vessel on the site, which is then emptied periodically. But a large storage tank like this does allow for a long retention time in many cases and for the generation of different types of odor. Now, the collected leachate is generally disposed of either by filling a transport truck of some type and trucking it to a local POTW, a local municipal wastewater treatment plant, or it can be hard piped directly into a wastewater treatment plant collection system. This was a system that we worked with a number of years ago, and I wanted to show you that I wanted to mention, first of all, that there were really two areas of odor emission. One was when they were filling the tanker truck at the landfill site itself, and of course the more critical spot was where the tanker truck discharged into the city sanitary sewer system. So that unloading site was often an area of odors as they were being released. We ran a laboratory screening test using the shake test that I had showed you earlier. And you can see that we can get the hydrogen sulfide to come down pretty dramatically by adding permanganate directly into the leachate. In this particular case, the untreated leachate was quite high in sulfides, upwards of 2,500 parts per million. But remember again, this is in the shake test where we have a very small headspace above the jar, in the top of the jar, and we can concentrate sulfides to quite a high level. I'll back up and say that in this particular case, we did treat the 55,000 gallon storage tank in order to oxidize the sulfides before we pumped and filled the delivery truck. The sulfides were gone then, and the tanker truck, when it discharged in the city, did not have any odor associated with it anymore. So here's another case study that was very similar to the previous one, except in this case, we're talking about a landfill site that was actually located up in Canada. 30,000 gallons of leachate was collected in 3 on-site storage tanks, and it was hauled away using a tanker truck to a nearby municipal water reclamation facility. And in the last case, the same situation occurs here. Odors are released when the leachate is pumped and transferred. And in particular, hydrogen sulfide was being released when the leachate was transferred from the tankers to the city or municipal wastewater treatment facility. And at that site, atmospheric sulfide concentrations as high as 100 parts per million were measured, which creates a safety hazard for the driver who's discharging the leachate, but also, of course, a nuisance odor situation as well. So the solution was to add CARUSOL liquid permanganate directly to the leachate, and you can see the results that were generated below. So starting with no treatment at all and greater than 100 parts per million of hydrogen sulfide, you can see that as we increased the amount of permanganate fed, then the sulfide residual dropped quite dramatically. So somewhere in the range of 100 to 150 parts per million of permanganate. We're getting the sulfide levels down to a low enough concentration that it's quite possible that at the discharge point where the tanker truck is unloading, there was no nuisance odor situation anymore. In a recent treatment study that we ran, we have a little bit more information and a little bit more interesting look at what was going on. So in this particular case, a landfill was operating with one open cell and 3 closed cells at their particular site. And of importance in this case, they accepted construction and demolition waste into their open cell. Now, construction waste is important because it often includes drywall or wallboard that was manufactured using gypsum as the solid cement material, and gypsum is calcium sulfate. So under anaerobic conditions, that sulfate can be reduced by anaerobic bacteria, and sulfide is the byproduct of that reaction. And you can see the reaction that I've put on this slide, showing sulfate in the presence of organic material, which supports the bacteriological activity, and anaerobic conditions. So there's no oxygen present in the system anymore after holding the leachate for some time. The bacteria reduces that sulfate to produce sulfide in solution, and eventually, based on the pH of the wastewater, hydrogen sulfide that can be released into the air. In this particular case, the collected leachate is discharged to a local municipal water reclamation facility through the plant's collection system, so it's hard piped to that particular collection system. And odor complaints were being received from the neighboring community at the point of connection and also downstream of that point of connection within the city itself. And it was determined that hydrogen sulfide was the primary odor compound. Now here's some particulars on the leachate collection system. So leachate flows intermittently as it is collected and held below the open cell in a rather large wet well. When operating, the leachate flow rate is 32 gallons per minute. So the leachate transfer pumps have a capacity of 32 gallons per minute. And typically that pump runs 6 to 8 hours per day, and they run it usually 2 times each week. Now the leachate pump lifts the wastewater to a high point on the property, the highest elevation on the property, where it then transitions to a gravity flow system where it drains to the city. And hydrogen sulfide, of course, is released at points of turbulence within this piping system. So certainly at the force main discharge point, and also any bends or turns in the gravity portion of the system will also create turbulence, releasing the hydrogen sulfide. Now there were several treatments that had been tried, including hypochlorite bleach was used as an oxidizing agent, as well as hydrogen peroxide in an attempt to control the odors. But the addition rates were quite high for both of these compounds, and the odor control was really rather a mixed bag. And when hydrogen peroxide was fed, what we've been told is untreated sulfide emissions were running about 1,300 ppm as atmospheric H2S. And in the first and second manholes downstream of the pump station is where they were being measured. Now it could have been that the hydrogen sulfide was actually higher than 1,300 parts per million, but that was as high as the analyzer could read, and so we know that it was at least that high, if not quite higher. Now the operator has told us that the leachate flow with treatment with hydrogen peroxide, and they were using 35% hydrogen peroxide in this case. The peroxide usage was about 18 gallons or almost 59 pounds of peroxide per hour, which was a dosage of about 3,600 milligrams per liter. But at many times, the sulfide levels in the atmosphere were still continued to run at greater than 1,000 parts per million. Now, to visualize this system a little bit better, I've put together a very simple diagram that shows the wet well beneath the open cell and the leachate lift pump. But of particular importance on this diagram is the junction box where the force main discharges, which is also used as the chemical addition point. And then from there, from the junction box, the wastewater flows by gravity only a short distance, really less than 100 yards, to a gravity system manhole. And the nice thing about this is it allowed a perfect location for monitoring sulfides, either if it was untreated or if something was being added, some chemical addition was being added to the junction box. And here's an actual photograph of that particular manhole. On the left, you can see is the odor log analyzer that we're going to suspend in the headspace of the manhole. And then on the right, you can see the cover that is closed and the cord that is running and tied off on the electrical box supports. And that's what's holding the odor log in the headspace of this particular manhole. So the odor logger that we put in there, we first tried to monitor and measure sulfide levels without any type of treatment at all. And you can see almost within seconds the hydrogen sulfide level exceeded 1,000 parts per million. In this particular case, we were using an odor log that only measured within a 0 to 1,000 part per million range. So we could not tell how much higher than 1,000 parts this was actually running on this particular day. And I can tell you, just as an aside, we destroyed that hydrogen sulfide analyzer by exposing it to those sort of concentrations. Now, when we wanted to do our treatment, we brought in a very simple portable feed system. So the permanganate, liquid permanganate was delivered in a IBC or tote container. And then we used a small LMI metering pump that operated in, I think, a maximum of 8 gallons per hour was this particular pump that we set up for this particular treatment system. And during the test, during the initial shakedown of the system, we were running in the 2 to 5 gallon per hour dosing range. And these are the results that we collected. I mentioned that we used the odor logger to log data over several hours or several days. And this is what we found. So initially, by the red line, by the way, is the CARUSOL feed rate, it's actually in gallons per hour. Sorry about that typographical error. And the H2S is shown in the blue peaks and valleys that are also depicted on this diagram. So initially we were feeding at something less than 2 gallons an hour, and you could see that we were getting very good results, very low sulfide concentrations. At one point then we decided to turn the pump off just to make sure we still had a leachate flow that had a significant amount of sulfide in it, and you can see when the pump was turned off, the sulfide levels immediately increased to above 1,000 parts per million again. So the pump was turned back on at just over 1.5 gallons per hour, and we were getting some control, although there were peaks at various times which were rather high at this particular location. So as much as 300 parts per million or 100 parts per million were not uncommon. At that point, the permanganate feed system was turned off again, just to be sure we could see that sulfide was still being released by the leachate. And sure enough, when the permanganate was turned off, the leachate immediately releases hydrogen sulfide into the manhole headspace, and we can get readings up above 1,300 parts per million. So that satisfied us that the sulfide was still present and the permanganate feed system was turned back on. And it was stepped up gradually to as much as 5 gallons per hour before we were able to start getting the sulfide levels to drop back down again to very, very, very low, very low atmospheric levels. And then after we got the system back under control, the CARUSOL feed rate was turned down again to just about 4 gallons per hour. And it would maintain there with very, very good hydrogen sulfide results. So we thought this was quite a good demonstration of how permanganate would work in this type of leachate situation. So since that initial test, the permanganate feed system has continued to be operated by the on-site plant people. They report to us that the treatment is working well with no odor complaints from the city. They've actually optimized the feed rate now to 2 gallons per hour, and they've linked that feed pump, our chemical feed pump, to the leachate lift pump as well, so that it operates only when the leachate is being pumped. Measurements of atmospheric hydrogen sulfide at the connection with the city have been running at 0 ppm. They also report that there was a secondary, smaller wastewater flow that only operates at 2 to 5 gallons per minute on the backside of the property. That's also being treated now with CARUSOL liquid permanganate, and the feed pump is set as low as they possibly can set it, which is 1/4 gallon per hour. And they report to us that the secondary waste stream also can release very high levels of sulfides at various times as well. So the CARUSOL is reducing more than 1,000 parts per million of sulfide to basically down to 0. Now I want to finish very quickly here with just a couple of photographs of what permanganate packaging and feed systems tend to look like. So on the left you see the IBC, the tote, with a metering pump that is mounted directly on top of this tote. Often the metering pumps in a permanent system will be mounted to a shelving system or to a bracket attached to the wall so that the tote can be easily moved in and out when necessary. On the right-hand side, these are 55-gallon drums, high-density polyethylene drums that we can also ship liquid in for smaller application points or for areas where it's difficult to access and get chemicals in. So in this particular case, we're still using small metering pumps, and these are Stenner peristaltic metering pumps, which also work very well when trying to feed concentrated liquid permanganate. And then if the system is large enough and enough permanganate is being used, we can in fact deliver the CARUSOL liquid in bulk delivery trucks and offload it into a storage container. The permanganate is stable. It will be good for many, many months and is a very convenient way to handle and use permanganates at large system sites. So here is our contact information, and I'll turn it back over to Liz to finish up the webinar.
Great, thanks John. Just as a reminder to everyone, if you have any questions, go ahead and type those into the questions pane. We have some time, we'll get to those now. If you think of anything after, again, as John said, here's our contact information. Get in contact with us and we can get you those answers. So we have a couple questions that came in. What is the typical permanganate dose that you would see at a landfill?
Yeah, that's a great question. So it's very variable because the conditions are so different from one location to another. But they seem to be running, and in this last case study that I presented, it was running about 200 milligrams per liter as a dosage. And in some of the other ones, though, it can be quite high. So in that earlier case study, it was running as much as 1,000 milligrams per liter. The difficulty is that it's really hard to predict in advance exactly how much is going to be needed. because of other contaminants that may also be in the leachate as well. So the best way to really determine that is to do an on-site test and just do a screening to determine exactly what it looks like the dosage might actually be.
Okay. Another question is, can hydrogen sulfide reform if our retention times to the sewer is greater than 8 hours?
Yeah, that's a great question as well too. So the information that I've been able to research and look at is that yes, of course sulfide can reform because the sulfate is still there in the system. But it's a biological process, so it's not a very fast kinetics. Most of the research work that's been done looking at biological reduction of sulfate really looks at it in terms of really hours, many hours to days, really. So in an 8-hour system, I would not expect to see any significant amount of sulfide regenerated following the oxidation reaction.
Okay. And then a question, you mentioned that the addition of this product could cause flocculation. With that said, wondering if the addition of this chemistry would create solids, and if so, how are those solids typically handled?
Yes, so that's true. The manganese oxides precipitate out after the permanganate reaction, and you'll typically get about half of the permanganate weight in terms of manganese oxide solids. So if I'm feeding 100 parts per million of permanganate, I will generate about 50 parts per million of manganese oxide suspended solids. In these particular locations that we've been working with, they've actually moved the solids directly to the municipality, where the municipality removes those solids using their standard wastewater treatment primary clarifiers. I might add that we feed a lot of permanganate to municipal sanitary systems for odor control, and there's never been an issue with the manganese oxide. It always settles out well with the other solids that are present in the system, and there is no type of restriction due to toxicity on manganese or iron, so it does not pose any particular problem to the municipality.
Okay. And then we have one more question. So it's in reference, if you already have pumps, can the totes and drums be purchased? So yeah, John can talk about what we supply here from Carus.
Yes, we can in fact supply metering pumps that are compatible with the CARUSOL liquids products. And that's the only real caution that I would have about purchasing or using a pump that you may have on site, a metering pump. Is just make sure that the materials of compatibility are in fact compatible with concentrated permanganate. And we have a compatibility sheet that we update periodically. In fact, we'll be coming out with an updated sheet by the end of this year, I think. It will list all of the materials that we have used and tested, as well as materials that have been reported back to us by customers as being compatible with concentrated permanganate liquids. And we'd be happy to send you that guideline that we have put together.
All right, great. Well, again, we thank John for presenting today. Thank you for everyone attending. As we mentioned, if you would like a copy of the PDF or have any questions, get in touch with us. And be on the watch for our 2018 webinar schedule that we'll have on our website. Thanks, everybody.